Hi, I'm Catherine St. Jean, and this is Physics Lab 2, Motion of a Falling Object. The purpose of this lab is to track the motion of a slowly falling object or an object with drag. The models or principles we're using in this lab are Newton's second law and drag force. And a preview of the results is that in falling objects with drag, the drag force model is more accurate than just using Newton's second law. So here's my experiment. The system is the paper ball, and the surrounding everything else, including the floor, the earth. All right, so here are the fundamental principles used in this lab. On the left, first we have F net equals ma, which is Newton's second law. We have Newton's second law manipulated in terms of gravity, so the force of gravity is negative mass times gravity. We have the position update formula, we have the velocity update formula, and we have the drag force equation, which is where B is the proportionality constant, and V is velocity, and V hat, the entire equation is negative because V hat is in the opposite direction of the object's motion. So to model my experiment of dropping a paper ball, I put it into Tracker. Here's a screenshot of Tracker. Basically, I started with the initial position of the paper ball as soon as I dropped it, and then with a time step of 1/3 of a second, I tracked where the ball was every 1/3 of a second, and as you can see, the steps get further apart, showing the acceleration due to gravity, and Tracker also spit out on the right side of the screenshot, you can see the change in Y as the paper ball fell. So using Tracker and a tool where I can measure, since there was a ruler giving me an idea of how far the ball fell, I used Tracker to determine that the ball was dropped from a height of 0.785 meters. Because it was starting at rest, the initial velocity was 0 meters per second. So in line 39 and 40 of my code, those two facts are reflected. And then the second box of code, that is Newton's second law without drag force, because in line 70, you can just see F net is it's negative mg. In line 74 and 76, you can see my velocity update formula and my position update formula. And then in this bottom box of code, this is the coding that I used with drag force included. So in 71, drag force is included, and F net is weight plus drag combined. And similarly, I use the velocity update formula and the position update formula in my drag force code. So using the coding and the data from Tracker, I have 3 lines here on this chart. The blue line is the actual data from Tracker. The gray line is the predicted model from GlowScript with drag, and the orange line is the predicted model with no drag and just the force of gravity. So as you can see, the drag model is more accurate and closer to the actual fall of the paper ball. The paper ball did not accelerate as rapidly as the no drag model predicted. A potential source of error is that because I dropped the paper ball less than a meter, there weren't a lot of time steps. And if there were more time steps, maybe the data could have been a little bit more accurate. So what exactly does this mean? Well, if we know that terminal velocity happens when the force of drag has balanced out gravity pointing down, then we can assume that terminal velocity only happens in the model with drag. Terminal velocity did not happen in the model without drag because there's no force pointing upwards opposing the force of gravity. And on the top, we can see in the drag force model that the velocity is flattening out and approaching -2 meters per second. Similarly, on the bottom, where the object was thrown downward, I edited the code so that it had an initial velocity of -1 meters per second. It also approaches a terminal velocity of -2 meters per second. So Using the GlowScript code, we can deduce that both objects approach the exact same terminal velocity, but the one with a initial velocity of -1 approaches the terminal velocity a little bit sooner because it flattens out a little bit sooner.